Greetings and welcome to the Chemistry 151 lecture for Chapter 4, Part 2. In Chapter 4, Part 1, we looked at the balanced chemical reaction, and we looked at techniques how to solve that, how to balance the reactants and products, and we also looked at types of reaction. But in this chapter, we're going to see really the power of that balanced reaction and what it can do for a chemist, especially in an industrial setting where you're trying to make things, or also in a synthetic setting, like in an industrial or academic lab when you're trying to make new inroads into making new products, stuff like that. So without further ado, let's check this out. A balanced chemical reaction will show the relative amounts of reactants and products. So that may not seem intuitive at first because you see these numbers and you see the chemicals. But when you remember that all of those references are for moles, and moles can be related back to either grams or molecules, you can think of a way where you can figure out relative amounts of reactants you'll need and products you'll require. This is similar to a recipe in cooking. If you don't use the right amounts, you won't get the right product. Also, if you wish to double the recipe to make 2 cakes instead of 1, you can do that by doubling the different things. So this balanced chemical equation is for much more than just balancing math and math fun, shall we say. This section really exemplifies why chemists are employed by corporations, because people want to make plastic for their cell phones or wire for their computers or whatever, or food, all right, anything like that. And sometimes then you need a chemist to tell you how much you need, how much will be created. And of course, if the chemist converts it wrong, then they'll get fired, which is bad. It's cool. And the important part here is through the moles. And on the right-hand side, you can see this part right here where moles of something are being turned into something else. Moles of A is being turned into moles of B. And that's going to be the big-time part of this one. So let's get into this and see the secrets that chemists use to predict how much products will be created and how much reactants you'll need. Here's a reaction, 3 hydrogens, and it shows the ones don't usually show, but it's 1 nitrogen reacting to make 2 NH3. And NH3 is ammonia. And those numbers in front that we spent so much time figuring out how to balance in Chapter 4, Part 1 are very helpful, all right? It says that you need 3 moles of H2 and 1 mole of N2. And if they react, they will make 2 moles of NH3, all right? Now, it can be done for atoms and molecules, but honestly, that's not as exciting because people don't usually take individual atoms to make an individual molecule. They'll deal with moles of things at a time, like we talked about. So those coefficients are going to be really helpful. You need 3 moles to make 2 moles of NH3. If you only have 2 moles of H2, you won't be able to make 2 moles of NH3, but you can figure out the new quantities using that 3 to 2 ratio, the 3 moles H2 to 2 moles NH3. And you can do the same thing with the N2 as well. That's a 1 to 2 ratio. So if you have 1 mole of N2, you could make 2 moles of NH3. And if you had, for example, 2 moles of N2, you could make 4 moles of NH3. So hopefully you're kind of starting to see how this works out. And finally, if either H2 or N2 are expensive, you can also figure out the amounts of reactant you'll need. You would need like 1 mole of N2 to make 3 moles of H2. But if you only had half of a mole of N2, you won't be able to make 3 moles of H2. You'd have a smaller value. So those individual relationships among the coefficients are really, really important. Also remember the have no fear of ice clear brew or Hunkel-Briff, the 7 diatomics. They're going to be super important in this section. So going back, this is the reaction where propane is being burned to make CO2 and water. It's a combustion reaction. And again, there's 2 uses for that equation, all right? You can think about it in moles, which is what we do most of the time. So a mole of propane, C3H8, reacts with 5 moles of oxygen, and it makes 3 moles of CO2 and 4 moles of water. But you can also think about it, of course, on the atomic level. 1 molecule, C3H8, reacts reacts with 5 molecules O2 to make 3 molecules CO2 and 4 molecules H2O. And if you remember, you can convert molecules to moles using Avogadro's number. So for all of those, the proportional relationships between reactants and products would be the same. You would use Avogadro's number to go from moles to molecules or molecules to moles as needed. So the mole ratio is really a ratio of coefficients, and those coefficients are mole ratios. So if you're given grams and you turn it into moles using the molar mass, which we talked about in chapter 3, you can then use this mole ratio of the balanced reaction to turn moles of reactant into moles of product, or product into reactant, or whatever. Let's just say moles of A into moles of B. And finally, once you have moles of the new compound, you can then turn that into grams as well using molar mass. So this is kind of what it is. If A is going to B, let's say we know how many moles of A we have, we can use some kind of conversion factor to convert A into B. And that conversion factor, again, comes directly from the balanced reaction. And this is why we're spending so much time on it and stuff. So we can go reactant to product, or product back to reactant, which happens sometimes. Or you can even figure out how much reactant B you need if you only have so much reactant A. There's literally a ton of possibilities when it comes to this kind of conversion. The grams, moles, grams dance is something we're going to play a lot in this chapter. And grams, moles, grams sounds kind of weird, but you can see that up here we've got grams, then moles, then grams. So when I say grams, moles, grams, that means we're starting with grams of something we know. And we can turn that into moles of the same substance using the molar mass. And again, that's where the periodic table comes in. You look up the grams per mole, the elements, add them together, etc., etc. Then to go from moles to moles, or moles of A, what we know, to moles of B, what we're looking for, that's where the balanced chemical reaction comes in. We're going to use those coefficients to find it. And then finally, almost all the time, we'll go from moles of what we're looking for back to grams of what we're looking for. Most of the time in employer, industrial kind of situations, the people above don't really care about moles. They want to know grams and pounds and kilograms and things like that. So we'll go moles to grams back again. So notice in the grams, moles dance here, grams to moles, the first part, that's molar mass, and moles to grams is also molar mass. One time, in the first time grams of A to moles of A, we'll be dividing, but when we go moles of B to grams of B, we'll be multiplying by the molar mass. And the middle part, the moles to moles, that's going to come from the balanced equation. So when I'm going to say grams, moles, grams, this is where it's going to come from. So let's use an example to see how this works out. Nitrogen and oxygen gases combine to give nitrogen dioxide. And the question is, how many grams of oxygen are consumed and how many grams of nitrogen dioxide can be formed by the reaction of 133 gram of nitrogen in excess oxygen? Okay, that's quite a lot of information. So let's try and break this down. So this is obviously a chemical reaction. They got the names nitrogen and oxygen running around, so something to do with chemicals. Nitrogen and oxygen are the reactants. Those are the things that are combining, and they're making nitrogen dioxide, which apparently is the only product. And when you read through the second part there, we're starting with 133 grams of nitrogen. And the question here is how many grams of oxygen are consumed, which means how many grams of oxygen do we need to work with 133 grams of nitrogen? And the other part of this question is how many grams of nitrogen dioxide can be formed? So imagine that you are working at a chemical company and your boss says, all right, we got 133 grams of nitrogen, and let's pretend it's expensive. It's not really expensive because it's really abundant, but let's assume it's expensive. And your boss goes, okay, Russell, or whatever your name is, I want to know how many grams of oxygen I'm going to need to buy, and then how many grams of nitrogen dioxide I'm going to get out. So the boss would ask you this because they'd have to pay probably for grams of oxygen. And again, we have to pretend here that this is more exciting than it is, okay? But let's assume that that's it. They'd want to know how much oxygen they need to buy, and they'd also want to know then grams of nitrogen dioxide produced. And hopefully hopefully that would be then like a moneymaker, all right? So they can start making money and predictions and different financial models, things I don't understand working at a community college, let's be honest. But anyway, hopefully you see the idea. So in this problem, we're starting with 133 grams of nitrogen. And it says, how much oxygen do we need? How much nitrogen dioxide will we make? We have an excess of oxygen, so that means we got more than we need. But we do want to know how much it's going to take up. Now, there's going to be several parts to this reaction. We've got to figure out, of course, what a balanced reaction is. So important. We're going to go grams to moles and moles to grams of lots of things. And we're also going to use the balanced reactions relationships between N2 and O2 and N2 and NO2 to make this problem possible. Now, if you write out the reactants and products, it's nitrogen and oxygen making nitrogen dioxide. Now, remember, the 7 diatomics have no fear of ice clear brew or Honkelbrief, whatever. Nitrogen and oxygen are both diatomics. So those are going to be N2 and O2. Nitrogen dioxide is a non-metal compound where you can use Greek prefixes. Nitrogen dioxide means 1 N and 2 O's. So let's translate those out. It's N2 for nitrogen, it's O2 for oxygen, and it's NO2 for nitrogen dioxide. Okay, now we've got the raw reactants and products. So now let's see if we can balance this. Right now, the reaction is balanced for O2. So for example, there's an O2 on the reactant left side, and an NO2, there's an O2. But you can probably see that the N is not balanced because there's an N2 on the reactant side and only one N on the product side, an NO2. So we're going to have to first balance the nitrogen and then probably go back and look at the oxygen a little bit. So this is not a balanced reaction, all right? There's only one N, and there's 2 N's on the left. So the N's don't balance. The O's are okay, but the N's aren't. And it has to be completely balanced, all right? So again, what I would do is I would start by putting a 2 right there. Because if you do that, then the N2 on the left has 2 N's on the right, and that's cool. However, on the product side now, you can see that by adding that big 2, we have O2 and NO2, 2 times 2, 4 oxygens, and only 2 oxygens on the reactant side. So let's try putting a 2 right there. Now I have 2 times 2, 4 oxygens on the left, and 2 times 2, 4 oxygens on the right. And the nitrogens are balanced. You can absolutely check yourself, and I encourage you to do that. When you balance this out, definitely put the 2's down there. Now you can see that everything is balanced out and you should be good to go. So this is the reaction you want to use because all the elements that go in equal the elements that go out, stuff like that. If you're ever uncertain, once again, you can absolutely draw a line down the middle like we talked about. You can have N and O. On the reactant side, that 2 right there means 2 nitrogen, and 2 times 2 would be 4 oxygen. And if this is a balanced reaction, the product will be the same. 2 NO2s means 2 nitrogen, 2 times 2, 4 oxygens. Everything is balanced, good to go. On to the next step. So now let's go back to the 133 grams of N2. All right, and that is N2, by the way, that we've got. And what we're going to do is we're going to use moles here quite a lot. So let's turn the 133 grams into moles. And this number, 28.0, that's the molar mass of N2. If you look on the periodic table, nitrogen is about 14.00 whatever. I'm only using 3 significant figures because 133 is a 3 sig fig number. So you can see here if the molar mass of N2 is 28.0 grams per mole, I'm going to divide by 28 and multiply by 1. So that way the grams of N2 cancel out. And in your calculator, that comes out to be 4.75 moles of N2. Now that we have that, let's figure out the moles of oxygen required. Now, the last step where we saw 4.75 moles of N2, that was the grams to moles part of our grams to moles to moles to grams. And this slide now is going to be the mole to mole part. We have moles of N2, and let's figure out moles of O2 needed. Now, you could absolutely start doing NO2 first and then go back to O2. That's not a problem. However, for whatever reason, I decided to do oxygen first, so let's do it. But if you'd rather do NO2 and then go back to O2, that's fine. Now, once you have the moles of N2, one N2 is going to need two O2s. So what you can do is write a 2-to-1 ratio. And you can see there how the moles of N2 that you start are canceled by the 1 mole of N2 on the bottom. So again, top and the bottom will cancel, good old dimensional analysis, and the only unit left standing will be moles of O2. So in your calculator, 4.75 times 2, 9.50 moles of O2 are needed here to make this reaction happen. And moles are great, but most of the real world needs to know grams, which they can convert to pounds or kilograms or whatever. Now that we know how many moles of oxygen are needed, let's turn it into grams. We'll use the molar mass for O2. Oxygen is 16.00 on the periodic table, and because there's two of them, the diatomic, 16 times 2 is 32. We'll divide by a mole of O2, so that way the moles of O2 cancel out, and the only unit left standing will be grams of O2. So 9.50 times 32, it's going to take 304 grams of O2 to combust or react 133 grams of N2. So this number, 304, that we just figured out, that's the grams of oxygen we need to react with 133 grams of nitrogen. All right, if you put 304 grams of O2 in, that you'll need 133 grams of N2. And we figured that out again through that grams, moles, gram conversion. And that's what you need to do in chemistry. You have to go through the mole bridge where you go from reactant to product, or in this case, reactant to reactant. We also need to figure out how many moles and grams of NO2 are produced, all right? So going back to the moles of N2 that we started with, we can do another moles to moles relationship, but this time going moles of N2 to moles of NO2. In this case, it's also a 1-to-2 ratio like it was for oxygen, but this time we're looking at this 2. 2 moles of NO2 are created for every 1 mole of N2 that goes in. So 4.75 times 2 over 1. The moles of N2 cancel. It's the same answer as it was for O2. 9.50 moles of NO2 are produced. So this is another grams, moles, gram conversion, but this time it's from moles of N2 to moles of NO2. And the next step will be the one where we turn it to grams. If you look on the periodic table, a nitrogen plus 2 oxygens is roughly 14 plus 2 times 16, where 14 and 16 are the numbers for N and O on the periodic table. That comes out to be 46 grams, or 46 grams per mole. So if you multiply here, the moles cancel out. 46.0 times 9.50 to 3 sig figs, 437 grams of NO2 are created when 133 grams of N2 are reacted or burned in O2. So this number, 437, that's how much NO2 should be created if we put 133 grams of N2 in. Pretty cool. Here's another kind of question, and I encourage you to kind of go along with this problem and solve it while we're talking about it. This is a similar kind of problem with a little bit of a twist. First of all, the balanced reaction there is sulfuric acid plus copper, and it makes sulfur dioxide plus 2 waters plus copper 2 sulfate. And in this problem, we're starting off with 6 billion molecules of sulfur dioxide. Now, Let's look at that number a little closer. 6.0004 sig figs times 10 to the ninth. 10 to the ninth is a billion. 6 billion molecules of sulfur dioxide. And the question is, how many grams of water will be produced if that many molecules of sulfur dioxide are created? Now, that sounds like just a massive number of molecules, but remember, Avogadro's number, 10 to the 23rd, is what dominates these problems, and 10 to the 23rd is a lot bigger than 10 to the ninth. So in this problem, we will use the type of grams, moles, grams. All right, we're starting with sulfur dioxide, and we want to turn it into grams of water. But there's a little bit of a difference here because we're not starting with grams of sulfur dioxide, we're starting with molecules. No problem. Remember that the mole is right in the middle of grams, so you can go grams to moles using molar mass, but you can also go molecules to moles using Avogadro's number. And that's what we want to do on this problem. We're going to take the molecules of sulfur dioxide and turn it into moles of sulfur dioxide using Avogadro's number. And from there, we can use a relationship between sulfur dioxide and water, which is 1 SO2, invisible 1 right there, for every 2 waters. And then finally, we want to turn moles of water into grams of water, so we'll use the molar mass. So let's get started on this problem. First of all, you should always check that the reaction is balanced. And this one is balanced. If you don't believe me, which is totally okay, pause the video, put the line down the middle, make sure the hydrogen, sulfur, oxygen, and copper is balanced, stuff like that. And that's totally cool. This reaction is balanced. You'll need the ratio of water and SO2, and that's where the balanced reaction comes in. And so like we said earlier, for every 1 SO2, you're going to get, I guess, 2 waters. So there's a 2 moles water per 1 mole SO2 relationship. You're going to need the molar mass of the water, and that's how many grams per mole are in the water. So if you add up an oxygen and 2 hydrogens, that's about 18 grams. Better sig figs would be 18.02. And like we talked about earlier, you're going to need to go from molecules to moles, and that's where Avogadro's number comes in, 6.022 times 10 to the 23rd. In this case, it's molecules of SO2 per mole of SO2. So to solve it, and this is a very succinct way to solve it, we start with the molecules of SO2 and we turn them into moles of SO2. So instead of going grams to moles like we did in the last one, here we're going molecules to mole, just an alternate way to find the moles, no problem. So we'll take the billion molecules and divide by Avogadro's. Then we're going to go moles to moles, and that part is the same. That's the 2 moles H2O per 1 mole SO2. So we're canceling out the molecules in the first step. And the second step now, we canceled out moles of SO2 so that we've got moles of water. And then finally, to get it back into grams, we're going to multiply by the molar mass. So the moles of water will cancel and we'll have grams of water. Now, a note on your calculator, first of all. In your calculator, what I would do is I would write 6E9, so 6 times 10 to the 9th. That's a quick way to do it. I would divide that by 6.022 E23rd. If you use the E, it automatically sticks to the last number. If you want to write times 10 to the 23rd, then you should use parentheses. So you'd go divide parentheses 6.022 times 10 to the 23rd. Your call. Then I would multiply by 2. I would multiply by 18.02, and I should get out that answer right there. If you're not getting that answer, please take a screenshot of what you're doing and send it to me by email, and I'll look it over and maybe I've got some suggestions as to how you can get that. It would be really nice if in the real world, all of the reactant ended up as products, and that would be totally cool. But in the real world, that doesn't always happen. Sometimes the actual chemistry of the transformation is quite difficult or energy intensive, something like that, and you may not get all of the product out that you want. Sometimes when you're doing a reaction, a person makes a mistake. If it's a gas, maybe it leaks. If you're making cookies, maybe one falls on the floor and it can't be eaten, right? All of these things are reasons why what you think you're going to get out may not be the same as what you actually get out. So percent yield, which is this little thing down here, is a great way that chemists use to describe the efficiency, if you will, of their reaction. On the bottom is what they call theoretical yield, and that's just the number of grams you get out from the grams, moles, grams conversion. On the top part is something you get from the experiment yourself, and it's called the actual yield. So you actually have to do the experiment to see how many grams you get out. So the actual yield, how much you actually get in an experiment, which you can't calculate, you have to do the experiment, divided by the theoretical yield, which is how much you should have gotten out, times 100%. So let's see how percent yield works. So let's say that you're back to the original reaction we looked at earlier, where we had 133 grams of N2. And we calculated that the theoretical yield of NO2, which is how much NO2 we should get out, was 437 grams. Cool. So again, that 437 grams, that was a grams to moles to moles to grams conversion. That represents theoretically how much NO2 we should get out. However, for whatever reason, we only got 247 grams of NO2 out. All right, and this is something you have to measure in the experiment. This is what they call the actual yield. We didn't calculate anything, but we did the experiment, and this is how much we got out. So we can use those two numbers to calculate the percent yield of the reaction. Now, remembering that percent yield is the actual yield divided by the theoretical yield. 247 is the actual yield, and that goes on top. The theoretical yield, which is where the grams to moles to grams conversion thing comes in, that goes on the bottom. 247 divided by 437 times 100%. Percent yield, 56.5%. All right? So this reaction is 56.5% yield. Now, 56.5% could be an awesome percent yield, or it could be horrible, all right? Some reactions by default have percent yields that are almost 100%, if not 100%. On the other hand, I did some research in graduate school. I used some compounds which were very air and water sensitive, and the first time I did it, I think my yield was like 4.3%, and I was like so excited. I called my parents. I said, "Oh, I got the blue stuff to turn purple." And anyway, and they were like, "Oh yeah, okay, go back to bed. It's too late." But anyway, it was cool because no one had ever done it. All right, I was the first one, and it doesn't cure cancer or anything like that. But it was really cool chemistry. I still dig it. But neither here nor there. My percent yield was horrible. It was 4%. However, because it was the first time it was done, even my boss thought that was pretty cool. So anyway, percent yield is all over. It's not like A is 90% and higher, B 80 to 90%, that kind of thing. All right, percent yield is very specific to the reaction you look at. So just looking at this number, 56.5%, maybe that's good, maybe it's bad, who knows, but we can calculate it. And if we talk to other people making NO2, we could compare our percent yield to theirs and see how they related. Another thing that happens is that most of the time, if you have two or more reactants, one of the reactants is going to limit how much product you're going to make. Let's say you're doing a reaction with gold. Gold is an element, and you can do cool chemistry with it. However, as you can probably imagine, it's super expensive. So if you're doing a reaction with gold, and gold is so expensive, probably gold is always going to limit how much product you can get, because there's just not a lot of gold around, or it's so expensive to buy. So you're always going to be limited how much you've got. This brings up the idea of what's called a limiting reactant, sometimes called limiting reagent. And a limiting reactant is super important in chemistry because you might put in like a whole bunch of grams and think, oh yeah, I'm going to get a lot out, but the other thing is limiting what you have. So we're going to talk about what a limiting reactant is. We're also going to talk about excess reactant or excess reactants, all right, because those are in excess of what you need. The limiting reactant is truly a pivot point for chemical reactions. If you don't know what the limiting reactant is, you're going to be in trouble. The limiting reactant literally limits how much product you can make. And if you're looking at the excess reactant, you're going to quote, tell your boss, whatever, that you're going to make this huge amount of product when in fact you can't make that much. You have to limit it quite a bit. This is kind of a fun little slide right here. And you can see in this slide, there's hamburger patties. And I'm a vegetarian, so I'm going to say they're garden burgers, but you put in meat du jour, whatever makes you happy here. And these are hamburger buns, and these are slices of cheese. And if you're vegan, you can use a vegan cheese, whatever. Whatever, make it work for you, okay? It's really fine, all right? But anyway, let your instructor keep babbling, I guess. But okay, Prophet, back on. In this reaction, let's say that you and your friends come back after going to a concert and you're all hungry. And so you look in the fridge and, oh, okay, I've got 3 garden burger hamburger patties. I've got 6 buns and 12 slices of cheese. All right, cool. And your goal here is you want to make let's call it the ultimate burger. And in the ultimate burger, you have one of the garden burgers, all right? And you really like the cheese, whatever cheese you're using. So you've got 2 slices of cheese and 1 bun. So this product here you're making, all right, the ultimate burger, it's got a bun, it's got 2 slices of cheese and 1 of your garden burgers, all right? If you look at the buns by themselves, you've got 6 buns. So you're like, oh, right on, man. We can make 6 of these ultimate cheeseburger things. But obviously that's not going to happen because the garden burger hamburgers are limiting what you can have. Same thing if you look at the cheese. If you need 2 slices of cheese for one of these and you've got 12 a dozen, then you think you'd be able to make 6 of these burgers. But again, you're stopped because the hamburger patties are limiting here what you've got. So it's the hamburger / garden burger patties which you need to focus on as a chemist. You've only got 3 of them, and that's how many of these ultimate burger things you're going to make. So we would call the hamburger garden burgers there, we would call those the limiting reactants. They're limiting how much product you can make. And again, in this silly example, the product is this burger with 2 slices of cheese and a bun. The buns and the cheese I would call excess reactants or reactants in excess because there's more of those around than you need. At the end of the reaction, you're going to have 3 buns left and 6 slices of cheese, all right? And maybe you or your friends are into kind of like a cheeseburger, which is literally cheese and a burger. No burger itself. Cheese sandwich. My terminology here is stepping all over me. But anyway, you can see you've got excess cheese and excess buns left over. So knowing about the limiting reactant is pretty important. And it works in a lot of situations. And this is very silly, but hopefully you see the importance of it. If you look at just the buns, you'd say, oh yeah, we can make 6 burgers. But you don't have the garden burger / hamburgers to make that happen. Here's a chemical reaction. Doesn't make me quite as hungry. On the left-hand side in that box, all right, the red atoms are oxygen and the blue atoms are nitrogen. So on the reactant side in that box, you've got an NO here, an NO here, NO here, and NO right there. So you have 4 NOs, all right? And you also have one O2, which is the O and O together, a second O2, and a third O2. So you have 3 O2s and 4 NOs. And if you didn't look at the balanced reaction, you might think, oh, well, we got 4 NOs and 3 O2s. We have a lot more NO. O2 must be the limiting reactant. But if you let the chemicals react, you can see on the right-hand side, wait a minute, we've still got an O2 left, all right? That one hasn't been used. And the other ones have transformed there into NO2s. So this shows the importance, again, of the balanced reaction. You need two NOs to make two NO2s according to the balanced equation. So if you have four NOs, which we counted up earlier, you should be able to make four NO2s, all right? But for every two NOs, you only need one O2, all right? So you can imagine here that these two NOs need that oxygen right there. And these two NOs need the middle oxygen right there. And sure enough, there's an extra O2. And that's the one then that's left on the other side. So all of the NO was used up in this reaction. There's no more left over. And if it's not left over on the product side, that means it's the limiting reactant. So NO is the limiting reactant. There's nothing left on the other side. You run out of NO before you run out of O2. The oxygen is left over on the other side. You've got more of that than you need. So O2 is the excess reactant. Here's an example of how this works out. Zinc metal, let's say we have 7.00 grams with it. We're reacting it with 0.100 moles of hydrochloric acid, HCl. And in the process, we end up making zinc chloride, ZnCl2. Zinc is a positive 2 metal on the stairs, and chloride's negative 1. And we also make hydrogen gas, another one of the 7 diatomics. Let's find the limiting reactant, the reactant in excess, and calculate the theoretical yield of zinc chloride. Okay, so notice this problem is we're looking for a limiting reactant. So that answer will be either zinc or HCl. Only one of them can do it. And if we have a limiting reactant, which apparently we do, then there's going to be also a reactant in excess or an excess reactant. And the answer there will be zinc or HCl, the opposite of what we asked earlier. And then finally, once you know the limiting reactant, we'll go grams to moles to grams or some derivation like that to find what the theoretical yield of ZnCl2 is. Remember, theoretical yield comes from the limiting reactant. So we need to know how this works out. We have to have a balanced chemical reaction, all right? So zinc chloride, is ZnCl2, diatomic H2, zinc. We can make everything balanced by adding a 2 to the HCl right there. So we're good to go. So from this, we're going to turn zinc and HCl into something else and see which one limits and which one is in excess. You've got to get things in moles. So grams of zinc needs to be converted to moles. On the periodic table, zinc is 65.35, something like that, which would round up to 65.4. So you can see how grams of zinc on the top cancels grams of zinc on the bottom. 0.107 moles of zinc are present. And back in the original problem, you can see we had 0.100 moles of HCl. So let's convert moles of zinc into moles of ZnCl2, the zinc 2 chloride. And while we're at it, let's do the same thing, but starting with HCl and turning it into zinc 2 chloride. All right. So in this problem then, 0.107 moles of zinc, and zinc to zinc 2 chloride is 1:1. So the moles of zinc to moles zinc 2 chloride 1:1. We'll multiply by that. So 0.107 times 1/1 essentially is, big surprise, 0.107. The HCl is similar, except remember that HCl has a 2 right there. So it takes 2 moles of HCl to make 1 mole of zinc chloride. So 0.1 divided by 2, 0.05 moles zinc 2 chloride. Now, these numbers represent the zinc chloride that can be made, and you can see there's a heck of a lot less zinc chloride made from the HCl than there is from the zinc. Now, initially, if you look at those numbers, I mean, 0.100 moles of HCl, 0.107 moles of zinc, they look about the same. But because of that 2-to-1 ratio of HCl to zinc 2 chloride, you end up making a lot less zinc chloride from the HCl than you do the zinc. Going back to those things, the 7.00 grams of zinc created 0.107 moles zinc chloride, and the 0.100 moles HCl created 0.05 moles of zinc chloride. HCl is definitely creating less zinc chloride than the zinc does, all right? At 0.05 is a smaller number than the 0.107. Now, we could turn this into grams, but we can just stop it right here. We can see that zinc chloride is a lot less is being made from the HCl than the zinc. So that means that HCl is the limiting reactant. The HCl, this one right here, creates only 0.0500 moles of zinc chloride. So that means that HCl is limiting the product. That means HCl is the limiting reactant. The other reactant, which in this case is zinc, zinc is the excess reactant, or the reactant in excess. We have more zinc around than we need. There's going to be some left over at the very end. Once we know the limiting reactant, we can use those values to find the theoretical yield of the zinc 2 chloride. Now, usually theoretical yield is in grams, all right, sometimes moles, but usually grams. But the important part here, theoretical yield has to come from the limiting reactant. So we're going to go back to the zinc chloride from the HCl, the limiting reactant, which was 0.05. And we'll multiply it by the molar mass of zinc chloride, which is 136.3, to 3 sig figs. 6.82 grams of zinc chloride is the theoretical yield. In this reaction, we will only be able to make 6.82 grams of zinc chloride. And that's kind of cool to know. It's going to limit the product. We can only make 6.82 grams. If you would have quoted the 0.107 moles zinc chloride value, you would have had a completely different number. So let's say that you were ignoring the theoretical yield and limiting reactant, all that kind of stuff, and you started with the zinc chloride number, which was 0.107 moles. And that, again, that number came from the zinc. So in that case, then, you would say, oh yeah, 14.6 grams of zinc chloride should be made, and you might feel really cool. However, what you just did is you looked at the buns instead of the garden burgers in that last example. Remember how we said how there's 6 buns, so it makes it look like you can make 6 of those ultimate burgers? In reality, though, the garden burgers are limiting how much you can make. So zinc to zinc chloride gives you an artificially high number. Now, it's not as tasty, of course, as one of those burgers, but it's the same idea. You can't make 14.6 grams of zinc chloride here. You can only make 6.82 grams. And that's because the HCl is limiting how much product can be made. Just like the garden burgers limited how many of those big burger combination things you could make. Here, it's the HCl which is limiting the product. So it's a really important idea when it comes to chemistry. All of these things are grams to moles to moles to grams, some derivation of them, and it's not hard. Practicing is the way to kick this out. Of course, I'm here to help you at any time if you have questions too. This is a problem you can test yourself, and I encourage you to kind of pause the video as we go through this, and you can practice and just see what's happening. What we're going to do here is we're going to look at the reaction of how antimony 3 chloride can be made from antimony and chlorine gas. All right. Now, antimony is number 51 on the periodic table. The symbol is SB. So what we need to do here, if we're going to write a balanced reaction, we need to figure out what the heck antimony 3 chloride is, antimony and chlorine. So chlorine is one of the diatomics. Have no fear of ice clear, brew, or hunkel, briff, all right? Write it as Cl2, all right? But antimony is not one of the 7 diatomics. So we would write that as just SB. Now, antimony 3 chloride is assuming that antimony is acting more like a metal, which it totally does sometimes. Antimony 3 would be antimony plus 3. Remember, all of the metals that aren't in the 1A, 2A, and stairs are going to get a Roman numeral, so that would be antimony plus 3. Chloride is chlorine turned into an ion. Chlorine is in group 7, so to figure out the charge, 7 minus 8, negative 1 is the charge on chloride. So if you've got a positive 3 antimony and a negative 1 chloride, the formula for neutrality, SbCl3. So initially, you've got an Sb and a Cl2 and an SbCl3. We need to make sure, of course, that the chlorine's balanced because of that diatomic. So initially, you'd have a 2 by the SbCl3 and a 3 by the Cl2 to make that balanced. And then finally, rounding it out, we put a 2 by the antimony. Now in this problem, it shows that they're all gaseous, all right, which is totally fine. If you don't know the states of matter, it's certainly not the end of the world. But if they're there, it looks kind of cool. All right, I think it looks kind of cool. But again, I'm a chemist. All right. Let's say that in our reaction, we have 129 grams of antimony and we have 106 grams of Cl2. And we want to figure out the limiting reactant and the theoretical yield of the antimony 3 chloride. All right. So this is going to be a problem where you have 2 reactant amounts and we've got to figure out which of them is going to create less product, less SbCl3. And the one that creates less SbCl3 will be our limiting reactant. And the other reactant, of course, would be the excess reactant. And then from there, the lesser amount of SbCl3 made, whatever number that is, that's going to be the theoretical yield of the product. So on both of these, what I would do is I would go grams, moles, moles, grams. For example, you could start with 129 grams of antimony and turn that into moles using the molar mass for antimony on the periodic table. Then for antimony, you would use 2 moles of antimony on the bottom and 2 moles of SbCl3 on the top, so a ratio of 2:2. And then you could multiply by the molar mass of SbCl3. You do the same kind of thing with 106 grams of chlorine. All right, that number is what you'd start with. You turn grams of Cl2 into moles of CO2 using the molar mass. You would have, in that case, then a 3 Cl2 to 2 SbCl3 ratio. That would be the mole to mole part. And then finally, you'd go moles to grams. So this slide here has a lot of information, and you're welcome, of course, to pause at any time and see what's happening. But here's what's going on. The first part right here, you're starting with the antimony, and grams of antimony to moles of antimony, molar mass of Sb about 121.8. So that goes grams to moles. Then we've got the moles ratio, which again comes from the balanced reaction, this thing right here. 2 Sb's create 2 SbCl3s, so the moles of Sb cancel. And then finally, let's convert it into grams. So 228.2 is the molar mass of SbCl3. And if you do that calculation, 3 significant figures, 242 grams of SbCl3. That's the amount of product from the antimony. But because this is limiting reactant, we need to do a second grams to moles to grams, this time using Cl2, the other reactant. So that's what this next thing is, grams of Cl2 to moles of Cl2. Chlorine is 35.5 round times 2, 35.45 times 2, 70.9 grams per mole. Turning grams Cl2 to moles of Cl2. Then 3 moles of Cl2, need 2 moles of SbCl3 to turn into moles of antimony 3 chloride. And finally, same molar mass as before, we're going to turn moles SbCl3 to grams. And sure enough, look what happens, 227 grams, a smaller number than we had before, which was 242 grams. So what that means is that the Cl2 is creating only 227 grams, and the antimony is creating 242 grams. So because 227 is less than 242, that means that chlorine, which is the reactant that created the 227 grams, chlorine is the limiting reactant. And by default, the other reactant is going to be excess. So in this case, that would be antimony. And also importantly, the smaller number is really important, that 227. That's the theoretical yield of the SbCl3. That's how much we should make if this reaction goes well. When I do these kind of problems, I know it's a little bit more math, but I love going grams, moles, moles, grams for both reactants, or all reactants, however many you have. And I do that because, first of all, at the end, you're going to figure out which one automatically is the limiting reactant. The smallest product is the limiting reactant. You also can tell which one is the limiting reactant because the smaller number comes from the limiting reactant, chlorine, not antimony. There's a lot of utility for doing these kind of processes this way. Let's say we do that reaction and we collect 113.5 grams of SbCl3. And the question is, what's the percent yield for this reaction? And that's a really, really good question. Now, remembering that the theoretical yield that we calculated on the last slide was 227 grams, we can use these two pieces to find the percent yield. And percent yield, again, actual yield divided by theoretical yield. So the 113.5 number we had to do the experiment to actually get. 227 was a number that we calculated. Actual divided by theoretical. Percent yield almost always less than 100%. There's some rare times, like if the sample's wet when it is higher, it's not supposed to be, but anyway, once in a while you do get them. But anyway, most of the time less than 100%. So this percent yield, 50.0%, 3 sig figs because of the 227. So this is really cool. If you've got this process down, you're going to knock this stuff out. The more you practice, of course, the better it is. There's lots of different tools online, handouts and stuff. I can help you find some if you need any, so you just let me know. So that's it for Chapter 4, Part 2, where we see the power of the chemical reaction in quite detail and why it's so useful to chemists. And if you have questions on any of this stuff, please be sure and let me know. I'm more than happy to help you. Definitely reach out. Glad to have you here. Have a wonderful day.